Welcome back. In this lecture I shall discuss expansion devices used in refrigeration systems. So the specific objectives of this particular lecture are to list various types of expansion devices used in refrigeration systems, explain the working principles of capillary tubes and its salient features, describe analytical and graphical methods for selection of capillary tubes, and finally explain working principle and salient features of automatic expansion valves. At the end of the lesson you should be able to name different types of expansion devices, explain the operation, salient features, advantages and disadvantages of capillary tubes, calculate the required length of capillary tubes using simple analytical and graphical methods, explain the working principle, features, advantages and disadvantages of automatic expansion valves. Let me give a brief introduction. First of all, why do we need an expansion device in a refrigerant system? What are its purposes? The purpose of an expansion device in a refrigerant system is to first of all reduce the pressure from condenser pressure to evaporator pressure and to regulate the refrigerant flow from the high pressure liquid line into the evaporator at a rate equal to the evaporation rate in the evaporator. Now the evaporation rate in the evaporator is proportional to the load on the system. So when the refrigerant load on the system increases, the flow rate should be increased, and when the load reduces, the flow rate should be reduced. Okay. So the one of the main purposes of the expansion device is to of course reduce the pressure from the condenser pressure to evaporator pressure, which can be achieved easily. But the second task, that is to regulate the flow according to the needs, is more difficult. But this is also a function of the capillary tube. A function of the expansion device. Okay. Now the expansion devices used in refrigerant systems can be divided into fixed opening type or variable opening type. In fixed opening type, as the name implies, the flow area remains fixed, while in variable opening type the flow area changes with changing mass flow rates. So this is the difference between fixed opening type and variable opening type. There are basically 7 types of refrigerant expansion devices. These are: the first one is hand operated valves, second one is capillary tubes, third one is orifice, fourth one is an automatic expansion valve, fifth one is thermostatic expansion valve, sixth one is a float valve, and under float valve you have low side float valve, also high side float valve, and finally you also have electronic expansion valve. Out of these 7 types I am not going to discuss hand operated valves and orifice, because these are used only in some special applications. So I will be describing the remaining 5 types. I will begin this with the first one, that is a capillary tube. A capillary tube is nothing but a long narrow tube of constant diameter, and here the word capillary is actually a misnomer, because the surface tension effect is not really important in refrigeration applications of capillary tube. So it has nothing to do with the capillary effect, it is just the name. And as I said, it is a long and narrow tube. So what do we mean by narrow? Its inner tube diameters of typical capillary tubes range from 0.4 mm to 2 mm, and the length ranges from 0.6 meter to 6 meters. Now the pressure reduction in a capillary tube occurs due to the following 2 factors. Capillary tube is an expansion device, so obviously pressure reduction should take place across the capillary tube. Okay, so how the pressure reduction takes place in a capillary tube? That's how I am going to explain that. There are 2 factors which causes pressure reduction. The first one is the pressure drop due to frictional resistance offered by tube walls. And the second factor is pressure drop due to acceleration of refrigerant as it flows through capillary. So why the refrigerant accelerates as it flows through capillary? Because you know that when the refrigerant flows through the expansion device, a flashing of liquid into vapor takes place. So as flashing takes place, some vapor is generated, and since vapor has much lower density compared to liquid, the volumetric flow rate and hence the velocity increases in the direction of flow. Since the velocity continuously increases in the direction of flow, the refrigerant gets accelerated in the direction of flow. This requires a certain pressure drop. So the pressure, ultimately the total pressure drop across the capillary tube is because of the frictional effects and because of the accelerational effects. Okay. Now there are several combinations of length and bore for the same mass flow rate and pressure drop. That means if you want a particular pressure drop, let us say 10 bar pressure drop and a particular mass flow rate, you can choose any diameter and length combination. That means if you are selecting, let us say 1 mm diameter tube, then you get certain length. Okay, so this will give you the required pressure drop, and it will also give you the required flow rate. And you can also choose, for example, 2 mm diameter capillary and a longer length of capillary. Okay, or you can go for a smaller diameter capillary and a shorter length of capillary. Like that, there are many combinations of diameter and length are possible. All of them will give you, if you choose them properly, will give the required pressure drop and the mass flow rates. Okay, but of course there are certain practical limitations or practical constraints in final selection of capillary tube. Okay. Once a capillary tube of some diameter and length has been installed, the mass flow rate will vary in such a manner that the total pressure drop through it matches with the pressure difference between condenser and the evaporator. You cannot change it's a fixed area type, so you cannot change the cross sectional area. So once you select the capillary tube, then the mass flow rate always will match, so that the pressure difference across it will be the same as the pressure difference between the condenser and the evaporator. And its mass flow rate is totally dependent upon the pressure difference across it. It cannot adjust itself to variation of load effectively. So this is one of the limitations of capillary tubes. Now let us discuss an important concept that is called as balance point of compressor and capillary. A balance point is said to be reached between the compressor and capillary when at some condenser and evaporator pressures the mass flow rate through the capillary equals the mass flow rate through compressor. In fact, when you say that the overall system is balanced, what you actually mean is that the flow rate through all the components are same. Okay, for example, the flow rate through evaporator is equal to the flow rate through the compressor, which in turn is equal to the flow rate through the condenser, which is finally equal to the flow rate through the capillary. Okay, so under this condition you say that the system is balanced. So basically for selection of capillary, a matching between capillary and compressor is important. Okay, so when you say that compressor and capillary are balanced, that means the flow rate through the capillary is equal to the flow rate through the compressor. Okay. Now the mass flow rate through a given capillary increases when the pressure difference between condenser and evaporator increases. That means if m dot Cp, this is the mass flow rate through the capillary, this is always proportional to P condenser minus P evaporator. Okay, so as this difference increases, mass flow rate through the capillary increases. On the other hand, a mass flow rate through a given compressor increases when the pressure ratio decreases. This is what we have seen in fact while discussing compressors. That means mass flow rate through the compressor decreases as Pc by Pe increases. Okay, so the pressure difference has opposing effects on compressor and capillary. Now this picture shows the balance points between capillary and compressor. You can see that in here the x-axis is the evaporator temperature, and on the y-axis we have the mass flow rate of the refrigerant, and these solid lines are for the compressor. So you can see that for a given condenser temperature, let us say 30 degrees centigrade, as the evaporator temperature increases, evaporator pressure increases, so pressure ratio reduces, so the volumetric efficiency of the compressor increases. As a result, the mass flow rate through the compressor increases. Okay, that's what you can see here. Similarly, at a given evaporator temperature, as the condenser temperature increases, the pressure ratio across the compressor increases, volumetric efficiency reduces, so mass flow rate reduces. That's why you get this kind of three curves for the compressor. And as I said, for the capillary the characteristics are entirely different. For example, for a capillary at a given condenser temperature, let us say 30 degrees centigrade, as the evaporator temperature increases, evaporator pressure increases. That means Pc minus Pe reduces. Okay, so as Pc minus Pe reduces, as I have already explained, mass flow rate through the capillary reduces. So that is what is shown here. For fixed condenser temperature, evaporator temperature is increasing and mass flow rate through the capillary is reducing. Similarly, at a given evaporator temperature, as the condensing temperature is increasing, condenser pressure increases, pressure difference across the capillary increases, so mass flow rate increases. Okay. Now I was talking about the balance points. You can see that the points A, B, C are the balance points. Why do you call them as balance points? For example, at 30 degrees condenser temperature, this is the capillary tube line, and this is the mass flow rate through the compressor, and the point where these two lines intersect, that is this point. At this point, the mass flow rate through the capillary is equal to the mass flow rate to the compressor. So this is the balance point for this particular condenser temperature of 30 degrees centigrade, and the corresponding evaporator temperature is, let us say, TA. Okay. Similarly, at 40 degrees condenser temperature, point B is the balance point, because at point B the mass flow rate through the capillary is equal to the mass flow rate through the compressor, right, and the corresponding evaporator temperature is TEB. Similarly, point C is the balance point for 50 degrees centigrade condenser temperature, and TEC is the corresponding evaporator temperature. Okay. One thing you can notice here is that as the condenser temperature is increasing, the evaporator temperature at which the balance is taking place is also increasing. Okay. So, for example, TEC is greater than TEB and TEB is greater than TA. So, that is what is summarized here. For a given condenser temperature, there is a definite value of evaporator temperature at which the balance point will occur. A, B and C are the three balance points for the three condenser temperatures 30 degrees, 40 degrees and 50 degrees centigrade, and the evaporator temperature at balance point increases with increase of condenser temperature. I have already explained this. Now let us look at the effect of load variation. The load on a refrigerant system does not remain constant always. This we have discussed before. The load may increase or decrease. So what happens when the load increases or decreases? First let us look at what happens when the refrigeration load increases. When the refrigeration load increases, there is a tendency for evaporator temperature to increase. Why the evaporator temperature increases? Because once the load increases, more liquid boils, and so the evaporator pressure increases. As a result, evaporator temperature also increases. As evaporator temperature increases, mass flow rate through the compressor will be more than the mass flow rate through the capillary, because as the evaporator temperature increases, the pressure difference across the capillary, that is the condenser pressure minus evaporator pressure, reduces. Once it reduces, flow rate through the capillary reduces. At the same time, the pressure ratio across the compressor increases as the evaporator pressure increases. As a result, compressor will pump more refrigerant. Okay. So that means there is an imbalance. As a result of this, the evaporator will start starving. Okay. So what do you mean by this? That means you have the, let us say that this is the evaporator. Okay. So refrigerant is coming from the capillary, you have the capillary on this side and the compressor on this side. Okay. Let us say that this is the mass flow rate, inlet mass flow rate, and this is the outlet mass flow rate. Okay. So when the evaporator temperature increases, m dot O will be greater than m dot I. Okay. That means you are taking out more refrigerant from the evaporator than you are supplying to the evaporator. As a result, the evaporator will starve. Okay. Now this cannot continue indefinitely. There must be some corrective action. So what is the corrective action? The corrective action under increased load is like this. Refrigerant gets accumulated in the condenser. Because the evaporator starves, the refrigerant goes and gets accumulated in the condenser. Once refrigerant gets accumulated in the condenser, effective area for condensation reduces. As a result, condenser temperature and pressure increases. Once the condenser temperature and pressure increases, flow rate through capillary increases and flow rate through compressor decreases. Okay, so this is the corrective action. And a new balance point is established at higher evaporator and higher condenser temperatures. So let me show this. As I said, this is the, let us say that this is the initial balance point, and then there is suddenly increase in load. Once the load increases, evaporator temperature, as I said, increases. Let us say that this is the new evaporator temperature under increased load. Okay, TEC. So at this point, initially you can see that the mass flow rate through the capillary is much less than the mass flow rate through the compressor. Okay, so as a result, as I said, the evaporator will starve and liquid gets accumulated in the condenser. Once liquid gets accumulated in the condenser, condenser temperature increases. Okay, so the condenser temperature comes down from this point to, increases from this point to this point. Okay, So, if it is, let us say, to give an example, if this is 40 degrees centigrade and let us say that it becomes 50 degrees centigrade because of the accumulation of the liquid. So, this is the 50 degrees centigrade line. Okay. So, this is the new compressor mass flow rate line, and similarly this is the new capillary mass flow rate line, because as the condenser temperature increases, Pc minus Pe increases. Okay. So, mass flow rate through capillary increases. Okay. So, you find that the new line is, capillary line is this, and the compressor line is this. So, and again the point of intersection is here, where the mass flow rate through capillary will be equal to the mass flow rate through the compressor. Okay. So, again a new balance point is restored. So, one thing you can notice here is that before the load increased, this was the balance point. So, the new balance point under increased load is here, and this at this point you can see that the evaporator temperature is higher than the original point. That means TEC is greater than TEB. Similarly, the condenser temperature at the new balance point, that is condenser temperature at C is greater than condenser temperature at B. So, a new balance is the point is restored, but at much higher temperatures. Now, let us look at what happens when there is a decrease in refrigeration load. When there is a decrease in refrigeration load, there is a tendency for the evaporator temperature to decrease, because less refrigerant will boil. So, pressure will reduce, so temperature also reduces. So, capillary tube feeds more refrigerant to the evaporator than the compressor can remove. This again I have explained to you. Again you have the evaporator here. Okay, so capillary tube is here, and you have the compressor on this side. Okay, so the capillary tube feeds means more refrigerant enters and less refrigerant leaves. Okay, that means now m dot O is less than m dot I. Okay, that means the refrigerant gets accumulated in the evaporator. This effect is exactly opposite to what happens when the load increases. Okay. So, this leads to accumulation of liquid refrigerant in the evaporator, causing flooding of the evaporator. This may lead to slugging of the compressor, and as you know that slugging of the compressor is dangerous and it should be avoided, otherwise the compressor may get damaged. So, to avoid slugging, capillary tube based systems are critically charged. Okay. So, what do we mean by critically charged system? Critical charge is a definite amount of refrigerant that is put into the refrigerant system, so that in the eventuality of all of it accumulating in the evaporator, it will just fill the evaporator up to its brim and never overflow from the evaporator to compressor. That means when you say that the system is critically charged, what it means is the refrigerant that is inside the system and the evaporator volume are such that when you transfer all the refrigerant into the evaporator, all the refrigerant means all the refrigerant from the condenser and other components and all into the evaporator, still the refrigerant amount will not be sufficient to overflow from the evaporator. Okay, it may fill the evaporator completely, okay, but liquid will not overflow from the evaporator. So, what is the advantage of this? Since the liquid cannot overflow from the evaporator, there is no possibility of liquid entering into the compressor. Okay, because once the liquid enters into the compressor may get damaged. Okay, so this kind of a system is called as critically charged system. Okay, critically charged systems do not use liquid receivers, and critically charged systems use hermetic compressors to minimize refrigerant leakage from the system. Now, when you charge the system critically, that means you put the right amount of the refrigerant into the system. Okay. So, if there is any leakage from the system, let us say, then after some time you find that the amount of refrigerant inside the system is much less than what is required. Okay. That means the system will be running under less refrigerant. Okay. This will affect the performance in an adverse manner. Okay. So, whenever you have critically charged systems, you must minimize leakage. Okay. If you want to minimize the leakage, you cannot use open type compressors, because in open type compressors refrigerant leakage is higher. Okay. So, normally not normally, you have to go for hermetic or sealed type of compressor, so that refrigerant leakage from the compressor and from the system is minimized. So, all the critical charge systems use sealed compressors. Okay. Now, what is the corrective action under reduced load? Corrective action under reduced load is like this: the liquid seal at the condenser exit breaks and some vapor enters the capillary tube. Okay. This happens because Okay. So originally under design condition, this was the entry point to the capillary, because you have the capillary here, okay, evaporator here, compressor here and condenser here, right. But now under the reduced load, more refrigerant gets accumulated here, so there will be less refrigerant in the condenser, okay. This is the condenser, so there is less refrigerant in the condenser. So once there is less refrigerant in the condenser, typically a condenser will have a liquid field. That means, just to give a simple idea, you may have a field like this which will be filled with liquid, okay. This is required so that no vapor enters into the capillary tube. But when the load is less, this liquid field will be broken, okay, because there is less refrigerant in the condenser, and it is not possible to maintain the seal. Once the liquid seal breaks, the vapor possibility of vapor entering into the capillary occurs, okay. Now that means the new condition under less refrigerated load will be this, okay. This is in the two phase region, that means into the capillary some liquid plus vapor enter, okay. So you can see that under these conditions the refrigeration low effect is reduced very much, whereas the compressor power input remains same, okay. This is inefficient, right. So the vapor has a very small density compared to the liquid. As a result, the mass flow rate through the capillary tube decreases drastically. This is not desirable since the refrigeration effect decreases and the COP also decreases, as I have already explained. So to avoid this, a vapor to liquid subcooling heat exchanger is usually employed to subcool the refrigerant entering the capillary, okay. So this is how the capillary tries to get adjusted to varying loads, and you have seen that it is not very effective when the load is varying, okay. So the capillary tube is very effective when the load is constant, but once the load varies, then the balance point shifts to new points, okay, and when especially it is dangerous when the load reduces, because there is a possibility of flooding and the performance also gets reduced, okay. Now let us look at the selection of a capillary tube. What do we mean by selection of a capillary tube? Selection of a capillary tube means given all other parameters like given the refrigeration capacity, operating temperatures, compressor size, etc., and the mass flow rate through the system, all these things are known to us. We have to find the required diameter and the length of the capillary tube. This is what is known as the selection of the capillary tube, in such a way that it at the design point the mass flow rate through the capillary will be same as the mass flow rate through the compressor. That means at design point the system will be under steady state, okay. So that is what is explained here. For any new system, the diameter and the length of capillary tube have to be selected such that the compressor and the capillary tube achieve the balance point at the desired evaporator temperature. And there are analytical and graphical methods to select the capillary tube, but both these methods involve certain assumptions. So finally, for the fine tuning of the capillary tube, it is always done by using what is known as the cut and try method, okay. Now let us look at an analytical method. This is a simple analytical method, and it is suggested by Hopkins and Copper long time ago, okay. It is a one dimensional analysis, and the analysis is carried out under the following assumptions. It is assumed that the flow is steady, flow is incompressible, fluid is considered to be homogeneous, capillary tube is assumed to be adiabatic, gravitational effects are negligible, okay. So under these assumptions the analysis is carried out, and this picture shows the control volume for selection of a capillary tube, okay. This is nothing but this here I have shown the section of the capillary tube which is vertical, okay. So this is the direction of the gravity is like this. So this is the vertical portion of a capillary tube, and this is the control volume which is a small section of the capillary tube, okay. It has a let us say that elemental height of delta y, and this is the inlet, right. So this is the inlet to the control volume, and this is the outlet to the control volume. At the inlet the pressure is P, at the outlet the pressure is P plus dou P by dou y into delta y. This is obtained by applying Taylor series expansion. Similarly at the inlet the rho V into V multiplied by the area is the momentum at the inlet, and this term multiplied by the area is the momentum at the outlet, and the tau W is the shear stress acting near the valves. Now we apply the conservation of mass for the control volume. So the conservation of mass, as we have seen earlier, is nothing but mass balance, and since we assumed the flow to be steady, you do not have the time terms here. So simply this term This entire term is nothing but the mass flow rate at the exit of the control volume, and this is the mass flow rate at the inlet to the control volume. Okay. So, in steady state whatever mass is entering into the control volume must leave the control volume, that is the statement of conservation of mass for steady state. Okay. So, this term gets cancelled, and finally you find that dou rho v by dou y is equal to 0, and that means rho v is constant, and rho v is nothing but mass flow rate divided by area, and this is equal to what is known as mass velocity g. Okay. So, finally the conservation of mass states that the mass velocity g through the capillary tube remains constant. Okay. Now, the next we have to apply conservation of momentum, and what is the conservation of momentum? Conservation of momentum simply states that momentum out minus momentum in, that means momentum at the outlet of the control volume minus momentum of the fluid at the inlet to the control volume is equal to the net force acting on the control volume. This is a statement of conservation of momentum, linear momentum. Okay. So, we apply the conservation of momentum now. So, if you apply the conservation of momentum, you get this equation, and let me just show this control volume once again. Okay, as I said, this term multiplied by the area is the momentum at the inlet to the control volume, and this term multiplied by the area is the momentum at the outlet of the control volume. And what are the different forces acting here? One force acting is due because of the mass of the control volume. Okay, that means because of the acceleration due to gravity. So, that force will be acting in the downward direction. Okay, let us say that this is mass of, right, due to the mass of the fluid in the control volume. This is one force, and you also have force due to shear stress at the wall of the capillary tube. This also acts in the opposite direction. It tries to retard the flow of refrigerant. Okay, so this also acts in the downward direction, and the pressure acts at the inlet of the control volume in this direction, and at the outlet the pressure acts in this direction. Okay, so these are the different forces acting, and the momentum in and out, and the area, since it is cylindrical, the area is simply equal to pi d square by 4 or pi r square, where r is the inner radius of the capillary and d is the inner diameter of the capillary. So, if you apply this, you find that the conservation of momentum equation boils down to this. This is the momentum at the outlet of the control volume, momentum at the inlet to the control volume. This is the net pressure force acting, and this is the force due to the gravity, and this is the frictional force due to shear stresses. Okay. Now, if you neglect the gravity term, that means if you are neglecting this term, because this term is normally very small compared to the other terms, so you can neglect this term. Okay. And when you manipulate this equation, you find that this pi r square term get cancelled, and this term gets cancelled here with this term. So, finally you get this equation. Okay. This is the equation for the conservation of momentum for the control volume. Here, as I said, the tau w is the wall shear stress. Now, the wall shear stress can be written in terms of friction factor. Okay. And for simplicity's sake, we assume that Darcy friction factor for fully developed flow is applicable. Okay. What do we mean by Darcy friction factor for fully developed flow? Once the flow is fully developed, this term will not be there. Okay. This term vanishes for fully developed flow. Once this term vanishes, you find that dou p by dou y, okay, is equal to, from this equation, because this is 0, is equal to minus 2 tau w by r. Okay, so this is, let us say, that equation A. Then you also have another equation using the definition of the friction factor. From the definition of the friction factor, delta Pf, that is the frictional pressure, is equal to Fl by d into rho v square by 2. Okay. So, what we do is we replace this shear stress term by using this equation and using this. Okay. So, using the definition of friction factor, the shear stress term can be finally written in this form like this. Okay. Tau w is rho f v square by 8, where rho is the density, f is the friction factor, and v is the velocity of the fluid, right. And substituting this expression in the expression for shear stress, we finally get this expression. Okay, rho v dou v by dou y is equal to minus dou p by dou y minus rho f v square by 2d. And we have seen that from the conservation of mass, g is equal to constant. So, what we do is we replace v by g, that means we write this equation in terms of mass velocity g, because this is constant, right. So writing the momentum equation in terms of mass velocity, we get this equation, okay. And you can see that this term, that is the term on the left hand side, this accounts for the pressure drop due to acceleration. As I said, pressure drop in a capillary tube is because of the acceleration and because of the frictional effects. So this term accounts for the pressure drop due to acceleration, and this term accounts for the pressure drop due to friction, okay. F is the friction factor, and the total pressure drop, the dou P by dou Y pressure gradient, is a result of frictional pressure drop and acceleration pressure drops, okay. And we have to find out what is the friction factor, okay. We have to evaluate the friction factor. How do you find the friction factor? In a capillary tube, the Reynolds number increases in the direction of flow. Why the Reynolds number increases? Because the velocity increases in the direction of flow, so Reynolds number increases. As a result, the friction factor also varies along the tube. But what we do is, as an approximation for a small elemental length, we select an average value of the product F and V, okay. That means we take a small elemental length and we assume that for that elemental length this product is constant, or we take a mean of this thing, okay. Fe mean we take for the elemental length. So integrating the final momentum equation over a small length delta L, we obtain this equation, delta P is equal to Z into delta V plus Z by 2D into Fe mean into delta L. Again this term, this term accounts, this is the total pressure drop for the small element, and this is the pressure drop due to acceleration, and this is the pressure drop due to friction, okay. So the above equation can be written in terms of like this, delta P is equal to delta P acceleration plus delta P friction, and the value of friction factor depends on the type of flow, and for fully developed turbulent flow in smooth tubes we can obtain F from this equation. F is approximately equal to 0.32 Reynolds number to the power of minus 0.25. So if you know the Reynolds number, then you can find out the friction factor. Once you find the friction factor and you know other things, then we can find out what is the required length. Now let us look at the solution procedure. This is the model suggested originally, and how do we solve this? The solution procedure is like this. Now, as I said, we know what is the refrigerant used. We also know the evaporator and condenser temperature, and we also know the mass flow rate. So with these inputs we have to find the required diameter and length of the capillary tube. So let me quickly explain how this is done. Let us say that this is the capillary tube, okay, and the total length of the capillary tube is, let us say, LC, and this is the inlet to the capillary tube and this is the outlet to the capillary tube. So at the inlet, what are the conditions? We have the temperature some Tc and the pressure is Pc, which is nothing but the condenser pressure, and at the outlet is connected to the evaporator, so we know that the temperature is Te and pressure is Pe, okay. So all these things are known to us, temperatures are known, pressures are known, and we also know the mass flow rate, okay. So if you look at the temperature across the capillary, a temperature drop of Tc minus Te is taking place, right. Similarly, a pressure drop of Pc minus Pe is taking place across the capillary. We have to find out what is the required, what is the length of the capillary, so that this much amount of temperature drop and this much corresponding pressure drop can take place across the capillary, okay. So what we do is we break this capillary tube into several small elements. Let us say that to give an example, let us say Tc is 50 degrees centigrade and T is equal to 0 degree centigrade, okay. That means Tc minus T is 50 degrees centigrade, right. So I will take 50 elements of the capillary tube, that means I divide the capillary tube into 50 elements, and across each element 1 degree temperature drop takes place, okay. That means if the for this one, if this is the element 1, and here if the temperature is 50 degrees centigrade, at this point the temperature is 49 degrees centigrade, and at this point it is 48 degrees centigrade. So like that the temperature reduces in this direction. Finally when you come to this last point, the temperature is 0 degree centigrade, okay. So what I do is I take the first element, and for the first element what I do is from the given information I find out what is the length required, so that this 1 degree temperature drop can take place across the first element, okay. So that is delta L1, Okay. Then I move from first element to second element, and for the second element again I find out what is the length required, delta L2 required, so that the temperature can drop from 49 degrees to 48 degrees, and similarly for the third element find out delta L3, so the temperature drops from 48 degrees to 47 degrees. So I proceed starting with the inlet right up to the outlet, and I go on finding the elemental lengths. Okay, and finally if you add up all these elemental lengths, you find out what is the required capillary tube length. Okay, so this is the procedure. Okay, so let me summarize whatever I have explained. Of course, you have two unknowns, that is the diameter and length. So we always have to start with some appropriate diameter and then find out the length. Okay, from the known inlet condition to the capillary and refrigerant properties, find velocity V, mass velocity G, and Reynolds number at the inlet. Okay, that means let us say that our inlet condition is saturated. So I know this point. At this point, as I said, I know the mass flow rate. Okay, mass flow rate of the refrigerant, and I am assuming some diameter of the capillary. So I know cross section area. Okay, that is pi d square by 4 is the cross section area of the capillary tube. So I can find out the mass velocity G, which is nothing but m dot by pi d square by 4. Right. I can also find out velocity at the inlet, that means at this point V naught. V naught is nothing but mass velocity divided by density at inlet, rho naught. Okay, so I can find out V naught. Similarly, I can find out other properties like specific volume at this point, viscosity at this point, right. So all the properties are known because I know the state exactly. Since the state is known to me, we can find out all the points, and we can also find out the Reynolds number, rho Vd by mu. Once you know the Reynolds number, you can find out friction factor, because friction factor is equal to 0.32, Reynolds number to the power of minus 0.25. Okay, so this is the friction factor at the inlet. So likewise, I find out all the required quantities at this point. Okay, then what I do is I assume suitable temperature drop, as I have already explained to you. Once you assume the suitable temperature drop, that means you come to the point 1. Okay, so you come to the point 1, and if you assume that the process is isenthalpic, that means HO is H1, which is known. Okay, and this temperature is known because you are assuming a suitable temperature drop. So this temperature is known, so you can fix this state. Once you can fix this state, you can find out the saturated liquid and vapor properties, and you know the saturated liquid and properties, and you also know the enthalpy of the mixer. That means H1 is known to us, okay, and HF1 is known, Hg1 is known, right. Since all these three parameters are known, we can find out what is the dryness fraction or quality at this point. Once you know the dryness fraction, you can find out all other properties using the homogeneous model. Homogeneous model means you treat the two phase flow as a pseudo single phase fluid, and for example any property can be found as a weighted average of the saturated liquid and vapor properties. For example, the viscosity at point 1 is obtained as viscosity of the liquid, saturated liquid, and its mass fraction, that means 1 minus x1 into mu f1 plus x1 into mu g1. Okay, so this is the viscosity of the mixer, which is equal to the mass fraction of the saturated liquid into saturated liquid viscosity, mass fraction of the saturated vapor into saturated vapor viscosity. Likewise, you can find out all other properties. Okay. Now choose a suitable delta T for which the length required delta L has to be calculated, 0.1. Assuming isenthalpic expansion and the saturated properties of refrigerant at 1, find quality X1 V Re at 1 using homogeneous model. This I have already explained to you. For the first element, delta V is equal to V1 minus V0. You know V1 and you also know V0, so we can find out V1 minus V0, and delta P is equal to P0 minus P1, which are known to us, and FV mean is nothing but F0 V0 plus F1 V1 by 2, where F0 and F1 are the friction factors at point 0 and 1, V0 and V1 are the velocities at point 0 and 1. Okay. Hence we can find out the incremental length for the first step delta L, L1 from the momentum equation. The momentum equation is rewritten in this fashion. Okay. So if you rewrite the momentum equation, this is the momentum equation. Okay. So you take this term to this side and write everything in terms of for delta L. Okay, so take this term also onto this side. Then you get this expression. So we know the length of the first element. Then you proceed to the next element by choosing a second delta T and calculate length required for the second element delta 2 L2. Repeat the above procedure till the temperature becomes equal to T, okay, as I have already explained to you, and total length is the sum of incremental lengths. The above procedure can be improved by not assuming isenthalpic expansion for each element. You find that in actual case the flow through capillary is not isenthalpic, but the enthalpy reduces inside the capillary tube. Why the enthalpy reduces? The enthalpy reduces because from the energy balance equation at any point H1 plus V naught square by 2 is equal to H1 plus V1 square by 2. And we know that in the direction of flow the velocity increases, that means V1 is greater than V naught. Okay, that means H1 should be less than H1, H naught. Okay, so the actual line will be something like this. This is known as a Fano line. Okay, so the actual enthalpy reduces as the flow takes place through the capillary. Okay, and point A is known as choked flow condition, and I will explain this later. So you can improve, as I said, the above procedure by considering a non-isenthalpic expansion. That means we write the energy equation also in addition to the mass and momentum equations like this: H naught plus V1 square by 2 is equal to H1 plus V1 square by 2, and replace V1 by mass velocity G and specific volume V1. Okay, and that equation is written in terms of the dryness fraction X1, right. So you ultimately get this equation. In this equation we know all these things are known to us. Okay, this is known to us, this is known to us, known to us. So only unknown is x1. So you can see that this is a quadratic equation. So when you solve this quadratic equation, it will give you two roots and you have to select the root that is positive. Okay, so the positive root of this quadratic equation gives you the correct value of dryness fraction. Okay. Now during the calculations it may so happen that the pressure drop due to acceleration is greater than the total pressure drop. Okay, so there are some circumstances under which this will happen. This leads to a negative incremental length. Okay, that means under certain circumstances this quantity will be greater than this. Okay, but this equation must be satisfied always, and this quantity is greater than this means this has to be negative. Okay, so this must be negative. G cannot be negative, D cannot be negative, F and V cannot be negative. So the only possibility is delta L has got to be negative. That means the incremental length becomes negative. Okay, this actually has no meaning. Okay, so this kind of a condition is called a choke flow condition, and this condition occurs when refrigerant velocity reaches sonic velocity. Okay, that means the velocity of the sound at that point. And the fluid velocity cannot exceed the velocity of sound in a tube of constant diameter, hence calculations cannot proceed any further. Okay, there is a problem of choked flow, and the flow is said to be choked flow, and the mass flow rate through the tube has reached its maximum value for the selected tube diameter. Okay, that means if you plot the, you can see that if you are plotting, let us say that you are fixing the condenser pressure and condenser temperature, and if you are reducing the evaporator temperature or evaporator pressure and proceeding in this manner, let us say that this is the initial mass flow rate. As you are reducing the evaporator pressure, Pc minus Pe increases because Pc is fixed and Pe is getting reduced. So mass flow rate through the capillary, as I have already explained to you, increases. Okay, so this process goes on like this, mass flow rate increases continuously, but a point will come at which further reduction in evaporator temperature will not give any further rise in the mass flow rate. Okay, that means beyond this point mass flow rate remains constant. So this condition is what is known as choke flow condition. This happens because at this point the velocity of the refrigerant, okay, reaches that of the sonic velocity. Okay, once it reaches the sonic velocity, the velocity cannot increase further, so mass flow rate cannot increase further, so mass flow rate remains constant. This is a typical problem encountered in compressible flows, for example in nozzles, etc. And this is known as choking, as I said, and if choking occurs at interior point, the length of the tube from this point to the exit will offer frictional resistance, and pressure must decrease to overcome this. However, pressure cannot decrease because flow is choked, hence adjustment in inlet condition occurs and flow rate is reduced, so that the flow will always be choked at the exit of the tube with reduced mass flow rate. Okay. So for a capillary tube of constant diameter, choke flow condition represents the minimum suction pressure that can be achieved. And if further pressure drop is required, a tube of larger diameter tube should be chosen in which the velocity of sound occurs at larger length. So let me once again repeat this. To start the selection procedure, what we have done is we have assumed some diameter, okay, and we started calculating the required length. And let us say that you have selected some diameter and in such a way that you are encountering choked flow situation, okay, and so if you are encountering choked flow situation, increasing the length will not help. Right. So what you have to do is you have to go back and you have to increase the diameter so that the length can be increased and the velocity of the refrigerant can be reduced, so that sonic velocity does not take place inside the capillary. Okay. So this procedure is some kind of a trial and error kind of a procedure. Okay. Now let me quickly explain the graphical method for selection of capillary tubes. A graphical procedure for capillary tube selection is based on the data of Hopkins and Whitesell, and this is presented in ASHRAE handbooks. Here the mass flow rate for various inlet conditions through a capillary tube of 1.63 mm diameter and 2.03 meter length are presented graphically. Okay, for example, okay, so this is a typical graph where this is the x-axis is the inlet pressure, which is nothing but the condenser pressure, and y-axis is the mass flow rate through the capillary. Okay, and this data is given for a particular diameter of the capillary and particular length, that is 1.63 mm inner diameter and 2.03 meter of length. And the mass flow rate is given for different inlet conditions. One is the pressure, the other one is the degree of subcooling. Okay, for example, this curve is for 10 degree subcooling, this curve is for 5 degree subcooling, this is for the saturated condition. Here is for two phase entry, that means the quality is 0.05, here the quality is 0.1. So for different inlet conditions, mass flow rates are reduced, mass flow rates are given. For example, if you know the inlet condition, let us say that it is a saturated and you also know the pressure here. So you can find out what is the mass flow rate through this capillary, that is 1.63 mm and 2.03 meter length capillary, right. For any other inlet conditions also you can find out what is the mass flow rate. Now a companion chart is provided for other diameters and capillary tube lengths. Okay, so this is a companion this thing, because not necessary that your capillary diameter is 1.63 millimeter and length is 2.03 meters. Okay, you can have any other diameter and length. If you have any other diameter and length, the actual mass flow rate through that diameter and length is nothing but the mass flow rate through the standard 1.63 meter mm diameter capillary multiplied by a flow correction factor phi. Okay, this flow correction factor phi is given as a function of the length of capillary at different diameters. Okay, for example, if the length of the capillary is 2.03, let us say this is 2.03 meter, okay, and the diameter is 1.63 mm, then the flow correction factor will be 1, because this is a standard capillary and here the mass flow rate is same as the mass flow rate through the standard capillary. Okay. These plots are for choked flow conditions, and ASHRAE has also given corrections for non-choked flow conditions. Now let me quickly summarize the advantages of capillary tubes. It is simple and inexpensive. It does not have any moving parts, hence it does not require maintenance. It provides an open connection between condenser and the evaporator, hence during off cycle pressure equalization occurs. This reduces starting torque requirement of the motor, hence a motor with low starting torque can be used. This is one biggest advantage of capillary tube. When the system is off, that means when the compressor is not running, condenser pressure is much higher than the evaporator pressure. So the pressure equalization takes place through the capillary tube, because capillary tube is nothing but an open tube, right. So finally you find that during the off condition, if the sufficient time is allowed, the entire system pressure will be same. Okay, so when the compressor starts at the after the off condition, it has to start again as the same head back pressure. Okay, that means it does not require a lot of starting torque to start. Okay, that means you can use low starting torque motors. And this is ideal for factory assembled critically charged hermetic compressor based systems. Of course, a capillary tube also has some disadvantages. What are the disadvantages of capillary tubes? It cannot adjust itself efficiently to changing load conditions. This is what we have seen, and it is susceptible to clogging because of narrow bore of the tube. Okay, since the inner diameter is very small, if there is any impurity or some solid impurity or some moisture which may freeze inside the capillary, it will block the capillary and flow cannot take place. Okay, so cleanliness is very important when you are using capillary tubes. And there is danger of evaporator flooding and compressor slugging during low load and off cycle conditions, hence suitable for critically charged systems only with hermetic compressors. Okay, this I have already explained to you. Now let us look at the other type of expansion device, that is known as automatic expansion valve. An automatic expansion valve maintains a constant pressure and thereby a constant temperature in the evaporator. It consists of an adjustable spring and a follow-up spring. Let me show the picture of this. This is the schematic of an automatic expansion valve. This is also known as a constant pressure expansion valve. Okay, so this is the inlet to the valve. So refrigerant comes from the high pressure condenser and it flows through a strainer so that no dust particle or other impurities enter into the valve. So a strainer is used here, and refrigerant at high pressure enters here, and there is an orifice here. Okay, through the orifice the refrigerant flows, and finally it comes out from the valve and it goes to the evaporator. And here you have the evaporator pressure and here you have the condenser pressure. So all the pressure drop takes place across the orifice. Okay, this is very important to remember. So this orifice provides a very narrow opening, right? And the mass flow rate through the orifice, that means mass flow rate to the orifice is proportional to the pressure difference Pc minus Pe, and it is also proportional to the area of the opening. Okay, so if the area of the opening is high for the given pressure difference, there will be higher flow rate. If the area opening is small, there will be less flow rate. Okay. Now if you look at the schematic of the automatic expansion valve, it consists of a diaphragm, okay, or bellows, you can also use bellows, and an adjustable spring here and an adjustable screw. So using the adjustable screw you can adjust the spring compression, right? The spring constant can be, the force exerted by the spring can be adjusted with the help of the adjustable screw, and this is normally open to atmosphere, so atmospheric pressure also will be acting here. So now if you look at the force acting on the diaphragm, what are the forces acting on the diaphragm? You have one atmosphere force due to atmospheric pressure acting here, that is F0, and force due to spring, that is Fs. Okay, so the upward force is F0 and Fs. And what is the downward force? Downward force is, first one is due to the evaporator pressure, because as I said here the evaporator pressure acts because it is connected to the evaporator. So you have the upward force, that is evaporator due to evaporator pressure, and there is also an upward force because of the follow up spring, okay, that is FFS, right. And when the valve is balanced, these forces must be balanced. So at equilibrium the downward force, that is Fs plus Fo, is balanced with the upward force, that is Fe plus FFS. Okay. Now the valve acts in such a manner that the evaporator pressure remains constant as long as the refrigeration load is constant. At this point the mass flow rate through the valve is same as that through the compressor. So you have the balanced condition now. Now effect of load variation, what happens when the load increases? Let us say when the load increases. When load increases, evaporator pressure tends to increase. So to keep the evaporator pressure constant, the needle moves up and the refrigerant flow rate reduces. Okay, that means let us say that because of the increase in the load, this pressure increases. Okay, PE increases. Once PE increases, FE increases, right? That means the downward force increases. Okay, the downward force increases. Once the downward force increases, a balance will be restored at a higher position of the needle. That means the needle moves up. Okay, the spring gets compressed, and a new balance is achieved at a narrower opening of the orifice. Okay, that means when the load increases, the orifice opening becomes narrower. Once the orifice opening becomes narrower, the mass flow rate through the valve reduces. Okay, so once the mass flow rate through the valve reduces, the evaporator starves due to the narrow opening. Okay. So this is the mass flow rate curve for the narrow opening. So the mass flow rate reduces. This is the balance condition at which mass flow rate to the compressor is equal to the mass flow rate to the capillary. But because of the increase in load, the needle moves up and the opening becomes narrow, mass flow rate to the valve reduces. So the new point is this. So you are supplying less and you are taking out more from the evaporator. So evaporator starves. So you have the starving condition now. Actually this is opposite to what we require, because when the load increases we want the refrigerant flow rate to increase, but unfortunately in this valve opposite thing happens, mass flow rate reduces so that evaporator pressure is maintained. Now what happens when the refrigeration load decreases? When the refrigeration load decreases, evaporator pressure tends to decrease, needle moves down because the upward force is higher now, to allow more refrigerant so that the evaporator pressure remains constant. Okay, that means when the load reduces, more there will be more mass flow rate. Okay, so that the pressure is maintained. This is again contrary to what we expect, and this may also lead to flooding of the evaporator. Okay, and hence the valve is suitable only for critically charged systems. Okay, just like capillary tubes. And during off cycle, valve remains closed as pressure in evaporator increases. Okay, that means during off cycle, but this pressure will be higher. Okay, so the during off cycle PE will be higher because TE will be higher. So the higher force is higher in the downward direction. So needle will be moved up, and this orifice will be closed. So there will not be any mass flow rate. Okay, during the off condition. And this is how the pressure varies during off and on. Okay, during the off pressure increases like this, right, in this manner, and at this point the compressor is switched on. Once the compressor is switched on, evaporator pressure drops. Once evaporator pressure drops, the upward force increases now, the valve opens, refrigerant is supplied, so again the pressure drops like this. Okay, so this is how the pressure varies when you are using an automatic expansion valve. Now applications and salient features of automatic expansion valves. These valves are relatively simple and economical compared to other types of valves, and they are used in small systems up to 10 TR capacity with hermetic compressors. They are used in critically charged systems to avoid flooding of evaporator. They are used where constant evaporator temperature is required. Okay, this is very important use of this particular type of valve, because this always maintains the evaporator pressure constant, that means evaporator temperature constant. So it finds application in milk chilling plants and in water coolers, etc. In milk chilling plants and water coolers, etc., the most important requirement is that the temperature should not fall below the freezing point of the liquid. Okay, once the temperature falls below the freezing point of the liquid, for example in a water cooler, the water may freeze in the pipes. Okay, once the water freezes, then the pipes will burst. Okay, so this should be avoided at any cost. Okay, that means you must make sure that the evaporator temperature is not going below a certain point under any circumstances. Okay, whatever be the load, the evaporator temperature is not going down. So the only valve which can ensure this is the automatic expansion valve. So the automatic expansion valve is normally used in water coolers and milk chilling plants, etc. Of course, as you know, it has its own disadvantages, like it can lead to flooding and all, and it doesn't supply the refrigerant as per the requirement, because when the load increases it supplies less, and when load reduces it supplies more. So this is the disadvantage of this particular type of valve. But still, in some circumstances where the load remains relatively constant and where we require constant evaporator temperature, we use this kind of a valve. Okay. Now to conclude in this lecture, various types of expansion devices used in refrigerant systems are listed. Working principles and salient features of capillary tubes are discussed. Selection of capillary tubes by analytical and graphical methods are presented. And finally, working principle and salient features of automatic expansion valves are discussed. So I shall discuss the other types of expansion devices in the next lecture. Thank you.